All right, so today we're looking at finding the tangent function. Let's have a look at where it's coming from and why it's looking like it looks. So if we just remind ourselves when we introduced the tangent function, the angle is the slope of the terminal ray of a side in the unit circle. So we have one way in which we define tangent of theta as being the slope of the terminal ray, and the other one is the tangent of theta is the y-coordinate divided by the x-coordinate, or in other words, it's going to be sine theta over cosine theta. These are how we define it. So what we're going to be looking at on this one particularly is that it is the slope. So if we have a look at a few different angles, if we're increasing theta from 0 to 2 pi, what is happening with the slope? It's increasing. What does it start off at? 0. What does it end at? Undefined. So as we go up towards pi over 2 here, it's going to be undefined at that particular point. So let's just have a read of this limit notation here. This one. It's saying the limit as theta goes to pi over 2 from the left-hand side, or from values below pi over 2, the tangent of theta will approach positive infinity. So it's going to get bigger and bigger until it becomes infinite. What about from pi over 2 onwards? So from pi over 2 to pi, it's going to start off at infinity, and it's going to be coming down. Now, this value here, that slope, is it positive or negative? That slope is negative, isn't it? That slope is negative. So coming into pi over 2, it's positive infinity. But coming past pi over 2, it's going to be negative infinity. Sorry? Because we're looking at it from the perspective of the slope. Looking at it from the perspective of the slope. So can we write a limit statement for that? What would the limit statement look like? Have a go at writing it down. What's happening as we approach pi over 2 from values bigger than pi over 2? Danny, try and write it with a pencil on your paper. Have a go at writing the limit statement there. As it approaches pi over 2 from a value bigger than pi over 2. All right, let's have a look at our limit statement. So we're going to have the limit as theta approaches pi over 2 from values that are bigger than pi over 2 of tan theta. It's going to be equal negative infinity. So it's going to go from negative infinity down to 0. So then as we move into the third quadrant, it's going to pass 0. Are the slopes here in this quadrant positive or negative? Here they're positive again until we get up to this point here. So until we come to this angle here. What is this angle here? This is 3 pi over 2, this angle. So as we get to there, it's going to approach infinity. So can we sketch this? Well, let's start off with, let's have a look at what we do know. So as theta and tan theta, we could use the exact value table a little bit. We start here, we go at pi over 6, pi over 4, pi over 3, pi over 2. What are the values from the exact value table for this period? And we have somebody else. 0. What's the next one? What about a pi over 2? Undefined. Well, that undefined business, that is going to be giving us a vertical asymptote. We can't define the tan function at this point. That gives us a vertical asymptote. We've got 3 important points. We've got this point here. We're going to go through 0. Pi over 4 is very useful for us. That one's going to give us a value here at 1. The other value isn't easy to read on a graph, but this is going to give us a graph that looks like this. Then if you remember, it comes back from negative infinity down to 0 and then up to positive infinity by the time we got to 3 pi over 2. So we're going to go to our asymptote here on this one, and our graph is going to go through this point here at 0. It's going to go through this point here at 1. It's going to go through this point here at -1. And our graph is going to look like this. And then the pattern just keeps repeating. We're going to go from here down to 0. And we go through halfway across there. It's going to come down like this. Keep going. It's going to keep going in that direction. So this is a useful point for us for reference, because this is where we have an exact value that we can really read off a graph nicely. And this is pi over 4, 1. It's a very useful point. This point here is really useful to us, 0, 0. And this point here is useful to us. It's minus pi over 4, -1. Or you can use this point here, which is at 3 pi over 4, -1. So these points are kind of useful for us in sketching the graph. When it comes to finding our transformations, remember these values. All right, so what are we looking at next? So here we have the graph of the tangent function drawn for us, nice and neatly. Noticing these points here are really useful. This is where pi over 4, 1. This point here at minus pi over 4, -1, and the asymptotes. The asymptotes occur at regular intervals. What is the period of this function? What is the period? What is the period here? This period is going to be pi. What makes it really useful for this graph, in drawing the graph, is the asymptotes. Start by putting your asymptotes up when you're drawing a graph. When you're trying to interpret a graph, start looking where the asymptotes are. Find out your period first. Okay, so the usual format factors for the transformations. If we have it in the form of, with our different 4 transformations, A is going to give us a vertical dilation. A is going to give us a vertical dilation. B is going to affect the period. C is going to give us our horizontal shift. And the vertical translation is given by D. Let's have a go. All right, take a couple of minutes. See if you can work out what the transformations are that make this function. Let me just get there. Here we go. All right, so analyzing this graph. First up, we need to, the first place to start is let's look for the period. So the period we can find by looking at the length of time between any 2 of the asymptotes. So this distance here will tell us. This is 3 pi over 4 minus 1 pi over 4, giving us 2 pi over 4. So the period is equal to 2 pi over 4, or pi over 2. That means that B is going to be equal to, what's the period normally for this function? Pi. So it's pi divided by pi over 2. These pi's will cancel, and this will give us b is equal to 2. This will give us b is equal to 2. The important thing to remember here is the formula. The regular period for a tan function is only pi. Normally it's 2 pi divided by something for the sine and the cosine one to find the b value. But because the period of the original function is less, because the period of the original function here is less, then we are not, if we see it here, we are not dividing 2 pi by b. We're dividing pi by b. And that's because this period is only pi. That's one of the tricky things to remember for this one. So b is equal to 2. Next up, is there a vertical translation? Is there an vertical additive translation? Now, look for where the curve goes from concave up to concave down, or concave down to concave up. So here the curve is concave down. Here the curve is concave up. At that particular point, we transition. So because this transition from concave down to concave up is lying on the x-axis, then d is equal to 0. This is the point that we'll find our d in, is when it changes concavity. So here we can see that d is equal to 0. Next up, we can look for our b value. And if we look here, just zoom in on this type of a point. So this point here is difficult sometimes to see in our graph. This point here, look at the distance there and the distance here. Those two distances are the same width. So it's halfway between the change in concavity and the asymptote. In effect, we're looking at the point that's normally at pi over 4. Back to the exact value table and the useful graphs here for us, it's this point here. This point here is our useful one because the y value is 1. So that one happens halfway between this point here and this point here. This is the asymptote. This is where it changes concavity. And that point is halfway between. So this point is halfway between. It's at pi over 4, not... It's at pi over 4, so that means a is equal to 1. Have I messed? Oh, that's I'm on the wrong graph. I'm like, ooh. Okay, sorry. I was expecting it to be at pi over 8. It is at pi over 8. So this point here again, it's halfway between. It's at pi over 8, but the y value is still 1. So there's been no vertical dilation either. So a is equal to 1. Okay, so find the constants of A, B, and D. There we go. Only B has changed. Vertical dilation is really hard to see. A vertical dilation is really hard to see because depending on how you draw your scale on your y-axis, it'll look the same. So it really doesn't change much. But what does change is if we dilated by a factor of 2, then this point halfway between those two would be up at 2. But the graph is going to look exactly the same shape. And if you change your y-axis, you can't tell by looking at all. The graph, it just basically stretches it upwards a little bit when we dilate it vertically, and it's gonna look like this, going up like that. But you can, if you find the x-coordinates halfway between the change in concavity and the asymptote, and you find the y value at that point, you can calculate the vertical dilation. All right. Have a go at this question. 2 minutes for this. Okay, so in this one, the function is defined here. What is the period of h? So from our formula, we say that B is equal to pi over the period like this one. So we can rearrange this, and then the period is equal to pi over B. That's going to give us the period is equal to pi divided by 2. So our period is going to be pi over 2. It's basically half the period. The period is normally pi. So in this case, it's half the period for us. All right, have a go at this one. Try and find out what the answer is. Exam style question. All right, so what we're looking on this one is what is the new, how can you define the asymptotes, the vertical asymptotes? So just coming back to the original function, we can put up one like this for the original function here for the vertical asymptotes. What is the period of the function in standard form? It's going to be pi. So the first asymptotes are going to occur at pi over 2, that's this line here, plus periods of n pi, where n is an integer. So asymptotes occur at the x-coordinate pi over 2 plus n pi. This is how we can define the periodicity of the asymptotes. So here in this question, we are told that b is equal to 1 over 3. What's the period going to be? Is the period going to be 3 or is it going to be 3 pi? So we have pi over 1/3, which gives 3 pi. This is our period. So the first asymptote, now let me come from this perspective. So what type of a dilation have we got? We've got a dilation horizontally by factor 3. Everything gets moved across by 3. So the first period, in this case, we're going to dilate. We have this function where they're going to occur normally at intervals given by this. So if we multiply this by 3, then they're going to be at 3 pi over 2 plus n 3 pi, intervals of integer. That gives us C. Yeah.
It says on C that K is only a constant, not an integer. So are you misreading that?
Yeah.
Then how do you integer?
It would have to be an integer. That's a mistake. The rest of them say integer. Yeah, sorry about that one. All right, C. Okay, have a go at question 4. Okay, so we need to find the function that's drawn here. Let's start off by looking at what is our period. So here in the graph, we can draw a line from here to here. This is going to be the period, which is given by this asymptote minus the vertical asymptote here, which is 2 pi. So B is going to be pi divided by 2 pi. So that's going to give us B is equal to a half. Next, we want to find the point which is halfway between the two asymptotes. So halfway between the two asymptotes is this line here. Here we can see the change in concavity is occurring at 0, minus 2. So we have a vertical dilation of we have a vertical translation of D is equal to minus 2. We can see in this case that the correct answer is A. Okay, Have a go at these last questions to practice.
Those last questions. I know you're going to do really well right here.
Is he playing games?
He wasn't playing games.
Is he looking at ladies?
He wasn't looking at ladies.
What else would he do?
Hey, do you want to say or do you want? Yeah, he was looking at a picture of, was it Shaquille O'Neal? LeBron James and sketching pictures of LeBron James. LeBron James with the facial hair, not.
I'm guessing this is a man.
LeBron James.
I'm guessing he's a black guy as well by the name.
Black
American.
He's a basketball player.
Right.
He was also in the new Space Jam movie. LeBron James.
Okay, thanks for that one. You may beat him if you wish. Why?
He asked me to. So because he likes men, you know?
I think he likes to be.
I think he was
All right, let me do one or two of these for you, get you started a bit quicker. I'm going to give you 5 minutes for these, but what you want to do to start with is draw up your unit circle. Sorry, not your unit circle, we'll do that as well. Start with your exact value table. We've got pi over 6, pi over 4, pi over 3, pi over 2. This is our exact value table. And it's 0, 1 over root 3, 1, root 3, undefined. Next, sketch yourself a little unit circle, like this one. Sketch yourself a unit circle and just sort of look at where they're going to be. So let me take one, like, for instance, I'll take D here. So D is at 5 pi over 6. So where is that going to... 5 pi over 6 is just less than a whole pi. So it's not 1, it's at just less than a whole pi. 5 pi over 6 is going to be here. It's going to have... maybe I'll do it this way. So if you think about the shape of the graph, I'm practically teaching it now. Let me backtrack. I should be recording this because this is more useful. All right. Let me record. Oh, I am recording. Great. Okay. So what we're looking at here is, if we think about the shape of the graph, it goes up like that and it sort of repeats like this. So the exact value table is going to repeat in a similar type fashion. After pi over 2, so if we're going from pi over 2, our next value is going to be 2 pi over 3. 2 pi over 3. Then we're going to have 3 pi over 4. Then we're going to have 5 pi over 6, and then we're going to have 6 pi over 6, or pi. The values are going to cascade downwards. So here it's undefined at this one, tan theta, and then it comes downward, but from a negative value, so it's going to be minus root 3 over 2, minus 1 over root 3, and then 0. Then it's going to go up again in the same kind of a pattern, 1 over root 3, 1, root 3, undefined, as we go towards 3 pi over 2. All right, have a go at these questions. See if you can work out from those values and your unit circle what the different values are going to be. Okay, so 4 pi over 3. Where on the unit circle is that one going to be? So let me just do a unit circle. So on the unit circle, this is going to be about here. This one's 3 pi over 3. This is 4 pi over 3. So this one is going to be going upwards. So it's a positive value. and that one is going to give us root 3. 7 pi over 4, so we have to think where on the unit circle 7 pi over 4 is. So 8 pi over 4, where is that? That's 2 pi. So 8 pi over 4 is here. So this is just 1 pi over 4 less than it, so it's going to be here in this one. The tangent value is going, the slope here is negative, it's going down. So it's going to be a negative value, similar to pi over 4. So this one's going to be minus 1. One more. 3 pi over 2. Oh, sorry, that one's easy, isn't it? Undefined. This one's going to be straight down. Pi. That one's easy as well, 0. Pi over 2. Undefined. All right, last, to finish us off, let's have a go at this exam-style question. Sorry, Khaled. Okay, so firstly, we want to find out what our period is. We can see in the function that b is equal to 2 pi. So this implies that the period is equal to pi divided by 2 pi. So the period is going to be a half. So that means it's going to repeat itself every half. So that means we have to take one of these two because we've got a period there of a half and a period here of a half. So every whole number would give us our period. Now, if we look at the function, there's no horizontal translation happening here. There's no c value. So the first asymptote is going to occur at half of where it normally occurs. So our general form for our asymptotes is that they're going to occur at pi over 2 plus n pi, where n is an integer. This is our general form for our asymptotes. So when the period is a half, this means it's going to shift it. So instead of occurring at pi over 2, it's going to occur at a quarter. So this one is going to be b. So normally it would occur at pi over 2, but if we divide, if we divide through by 2 pi on everything, then pi over 2 becomes 1 over 4. Let me just do that for you. Pi. So normally the first asymptote, the vertical asymptote, is at pi over 2. So the vertical asymptote this time is going to be pi over 2 divided by 2 pi. That gives us, the pi's cancel, gives us 1 over 4. It's going to be a b. All right, we're finished there for today.